All right, welcome. Hope you all had a good break. Some updates on what's going on with this class. I know you're probably interested in the exam. Unfortunately, I don't have any information for you yet. All my TAs were also on break last week, so I did the best I could by myself, but it was very difficult for me to make it through all of the exams on my own. The good news is that my TAs are back, and we're making good progress, and so I'm hoping that we'll get those exams finished up this week, and hopefully I'll have some news for you on that on Thursday. I did get homework 2 graded over break, so I did manage to get that finished up. So your homework 2 grades have been posted. You can find the feedback on your repositories, so take a look at that. Let me know if you have any questions. If you didn't get a grade for whatever reason, let me know so I can figure out what the problem was, make sure that we get that taken care of as soon as possible. Any questions about assignments, grading, things like that? You do have homework 3 still out. It's due 1 week from today, so you got 1 week left to finish up the B+ tree implementation. And just as kind of a little roadmap, since we're sort of a little more than halfway through the semester, we've got, so besides homework 3, we've got, I'm hoping for at least 2 more assignments. So we're going to have one coming out next week on Tuesday, actually, which is going to be over today's material and Thursday's material. And then we're going to have another one after that, which is going to be on a totally different set of topics, totally different set of stuff. So we'll talk more about that a little bit later. And then, of course, we'll have a final exam at the end of the semester as well. Unless there's any questions, I'm going to go ahead and get started with today's material. We're talking about stuff that's a little bit different, now. So we're going to talk about this idea of transactions today. So let's talk about, Let's talk about our databases for a second. So far, up until this point, we've been focused primarily on how does a database function, right? How do I get data into a database? How do I get data out of a database? Questions like that. We haven't really been focusing too much on who's actually going to be using our database. So the question that I have now is, how many people do we expect to be using our database? Is it going to be just 1 or 2, like on the assignments? Probably not. It's going to be a lot. In a real-world situation, in a real-world application of a database, it's going to be a lot of people that are trying to use that database. Think about the large websites that you visit, the Facebooks, the Googles, right? Their databases are getting hit by thousands, millions of people all the time. All the time. And so, what are some issues that could happen if we take that into account? If we realize that I'm not the only one using the database, but we now have maybe lots of people using the database, what are some problems that you think might happen? Anybody have any ideas? Yeah. Data may change, I'm sorry? When you read it. So I could have 2 people trying to access the same piece of information, right? Very possible that that could happen. And one person might be trying to change that piece of information, the other person might be trying to read it. Or they might be both trying to change it, right? They might be both be trying to write that piece of data. So the question is, okay, how does that work? How do I resolve that situation so that both people are happy? So that both people get what they expect. Any other issues you can think of? Yeah.
If you're on our websites, then you're going to have severe lagging issue. I mean, how do you know who's reading from the database? Can everybody read from the database at the same time?
Yeah.
How long is it going to take for them to access?
So performance is another big issue, right? If I'm expecting lots of people to use my database, can I provide them with the information that they want in a timely manner without making them wait a really long time? I think we've all probably been to websites where you have to click a button and wait. It's not a pleasant thing. So we want to try to reduce that as much as possible. And so that's probably more along the lines of what we're going to be talking about into next week, but still something that we need to consider as part of this course. And so one tool that we have to help us with these kinds of issues is this idea of a transaction. And so what a transaction is, it's a logical grouping of operations. So think about the queries that we've seen that we've been writing in this class. I can write select queries, I can write inserts and deletes and updates and all that stuff, right? What a transaction does is it takes a collection of those queries and groups them together as a single unit. As a single unit. And so a transaction then provides a single atomic unit of execution. And what I mean by that is either all of the statements that I've included in the transaction are going to execute, or none of them are. None of them are. So I can't get into this situation where I have a partial execution. I can't get halfway down the list of stuff that I want to run and then say, all right, I'm done. I don't have to do the second half. Things like that. And so the way that we do this is by monitoring the pieces of information that are going to be affected by the queries that are part of the transaction. So it's important to keep in mind, what is the data that we're actually monitoring? Am I doing this on the row level, the record level? Am I doing this on the column level? Am I doing this on the page level? Like, what are the chunks of data that I'm actually monitoring to make sure that these potential problem situations don't occur? And the answer to this question, what am I monitoring, is yes, all of the above, right? It's all fair game. So to illustrate this concept a little bit more, I want to show you some examples of the kinds of problems that we're hoping to solve with transactions. And then we'll talk about transactions in a little bit more detail, how they actually work, how they're actually implemented. We've got two basic operations for each item. So if you want to think of items as a row for right now, that's fine. Just think of it as a single row or even a single cell within a row. I can read that value or I can write to that value. And so with just those two operations, let's talk about the kinds of things that might happen. So here's an example of two transactions. Got one on the left, one on the right. Transaction 1 on the left there is going to read item X. Now what is X? I don't know. It could be a row, it could be a cell, it could be an entire table. I don't really know, right? It's some item in our database. So I'm going to read it, I'm going to modify it, I'm going to do some arithmetic, and I'm going to write it back. Then I'm going to read a second one, item Y. I'm going to modify it, and then I'm going to write it back. And then I have a second transaction that you can see only does the modification on X. It actually doesn't touch Y at all. It just touches X. So in practice, let's consider the case that these transactions are both coming from two different people. They might be on entirely different sides of the world, right? They're coming from two different sources. I want to execute them both on the database, and for the purposes of what we're talking about, we're going to assume that both of these transactions show up at the database at basically the same time. So I'm a database. I get both of these transactions in that tell me to perform these operations, right? And now I have a problem that I need to figure out, which is, all right, I can't do these simultaneously. I can't do both of these things at the same time. So how do I execute these statements in such a way that maintains the integrity of the database, does not cause any potential conflicts, any potential issues with my database? So let's take a look at a few examples of what might happen. These are the same two transactions, right, that I looked at on the previous slide. They're spaced out a little bit differently now, right? I can't do them both at the same time, so I have to use a process called interleaving. I take some operations from this transaction and I mix them in with some operations from another transaction, right? And so you can see I read item X and perform modification for the first transaction, and then the next thing I do is I do the same thing with the second transaction. What's the problem? Yeah?
T2 writes its item and overrode what T1 did.
So T1 looks like it never happened. The modification that T1 made to X as far as we're concerned, looks like it never happened. Because T2 is going to write its value back after T1 does, so it's irrelevant. Whatever T1 wrote there does not matter, right? So consider, what would we want to happen instead? How would we fix this problem? How would we prevent this situation from occurring? What would we want to do? Yeah?
I kind of have a question about what you just said.
Uh-huh.
If T1 reads X and then, it never writes.
Yeah, it doesn't write it until later. Yeah. So what would be a better situation? What would we like to see instead of this? Yeah?
Probably wait till T1 writes X.
Yep. Wait for the write to happen first, and then let T2 read the value and modify it accordingly. Right? That's a better situation than what we've got up here on the slide. This is called the lost update problem because the update that T1 made to item X looks like it never happened. All right, let's take a look at another example. So we just said, okay, let's let T1 write its item back before we let T2 read it and modify it. So here we go. It's doing exactly that, right? What's the problem now? This is what we just talked about, as we said it'd be a better situation, but what's the problem now? Anybody know? Yeah.
T1 may at some point try to look back at the right item for X and say, hey, wait a minute, this is what I put in here.
So T1, notice T1 is a transaction. That means that the statements that are included as part of T1 are meant to be taken as a single unit, right? So if T1 later, like you mentioned, wants to look at X, or maybe there's another part of T1 that needs to modify X for a second time, for example, right? It's going to go back and it's going to say, hey, this value is not what I thought it was anymore. Or actually, I think perhaps a bigger issue, you can see this problem is labeled the temporary update problem, right? This time the full update happened. T1 wrote X back, but the transaction wasn't finished yet. There was still more work to do. And so we actually don't have a record. We actually don't have any log. We don't have any record that this update took place, because T2 is overriding that record before the transaction has finished, before we can record that the transaction has successfully completed. So this is another issue called the temporary update problem. Not the only ones that we can talk about, though. These transactions are a little bit different now, right? Transaction 3 over here is not one that we've seen before. It's performing an aggregation. It's doing a sum, so it's reading the values and summing them up. And so the problem you can see here, incorrect summary problem. Consider what's happening. Transaction 1 is modifying X while transaction 3 is performing a sum that uses that value of X. So what happens is that when transaction 3 is finished performing its aggregation, the sum that it has computed does not actually match the true sum of the values that are now in the database, because transaction 1 has changed one of those values. So if I, as a human, go back and I try to verify, right, that this sum is correct, it's going to look like it's not correct, because transaction 1 has modified that value and it has invalidated the sum that I just computed. And then last but certainly not least, we've got an unrepeatable read problem. So if I have a transaction that reads the same value multiple times, and some other transaction is modifying that value in between, right, I'm going to see different values come back. If I read a row, and then I wait a little bit, and I read another row, I expect to get the same values back. But if somebody modifies it in between, I have what's called an unrepeatable read. I performed the same read twice, and I got two different values. That's undesirable behavior. That's unexpected. That would cause us to be surprised if that happened to us in real life. So these are all situations that we're aiming to avoid. Sometimes we can avoid them, though. Sometimes they're difficult to avoid, but we can talk about some techniques that we can use to help out with these problems. So let's talk a little bit more about transactions. The way transactions work is that all statements that are within a transaction must be executed, or none of them are. It's an all or nothing proposal. So if I look at these transactions from the previous slides, right? Any of these transactions, I want all of the statements in T1 to execute. And if there's a problem for any reason, I need to undo what I've already done. It's all or nothing. Consider a more practical use case for this might be something like inserting a bunch of data into your tables. So if I'm inserting a bunch of records, a bunch of rows into my tables, some of those might involve, primary key, foreign key relationships perhaps, right? And if I only insert half of them and I don't insert the other half, then I might have relationships that are poorly defined, that aren't completely defined, because the other side of that relationship wasn't properly inserted. I can use a transaction to prevent that scenario from happening. I can put all of those insertions inside of a transaction, which then says, all right, you can't just do half of these. Either all of these insertions have to happen, or none of them are going to happen. Oops, sorry. And so the question then becomes, okay, what happens then if a problem occurs? So if I have some kind of an error, I'm executing a transaction, doing one statement, then another statement, then another statement. Sometimes problems are going to happen. Sometimes errors are going to occur. I need to then go back and look at what I've done and undo all of those changes. If I successfully make it to the end of a transaction, I've executed every single statement that's contained within that transaction, I then perform a commit, which is basically saying, I verify that these changes all took place, right? And then I'm going to make a record of that. I'm going to write that fact down. I'm going to log it. Say, this is what I just did. Here's everything that I just modified. This all happened. It's now part of the official public record for this database. What are some problems that could occur that could cause a transaction to fail partway through? Anybody have any ideas? What are some issues that might cause a transaction to fail partway through? Go ahead.
Power goes out, cuts you off.
There you go. Natural disasters, right? It's an extreme case, perhaps, but it happens. It happens. You lose power, the machine shuts down, there's some kind of problem with the operating system, right? That's not the only kinds of problems that could happen. What are some other kinds of problems that could happen? Yeah. So somebody else is messing with the data, right? Causes some problems. Could happen. We're going to talk about other techniques that prevent that from happening a little bit later on. But yeah, stuff like that can happen. I could have an error in the code that I wrote, right? Maybe the query that I wrote isn't actually correct. So the transaction is going to run through. Eventually it'll hit this bad one, this bad statement that I gave it. And they'll say, oh, I don't know what to do with this. So it's going to fail that statement, but then it has to go back and say, all right, the whole transaction's failed now, and undo everything that it had done up until that point. It's just a small sampling of the kinds of issues that we might expect. So here are the states of our transaction. Every transaction that we create, every transaction that we run is going to follow a similar set of behaviors. I have a begin state where we fire up the transaction. I'm going to then perform my reads and writes. The next two might seem redundant. There's an end transaction and a commit transaction, right? But I think it's important that they're separated. End transaction means that I have finished all of the statements in the transaction, but I'm actually not done yet, because a committing the transaction, is actually making a record, writing a log of the transaction that has just taken place. So if I have not properly logged the end of my transaction that it's completed, that transaction technically is not officially completed. That's why those two states are considered separate. And then a rollback state is the issue for when a problem occurs. That's what we call it when a transaction needs to undo its prior work. We call that a rollback. So the state diagram for a transaction might look something like this. All right. We'll begin our transaction, perform our reads and writes. As soon as we're finished, we say it's partially committed, so the transaction's over. It's partially committed while we make the log, and then once we log it, it's done. It's now part of the public record and the transaction's over. If a problem occurs at any point along the way, you see we go to this failed state, which is going to cause us to roll back the transaction. So I've mentioned the log a few times. Let's talk about that in a little bit more detail, because it's a very important part of this whole process. Log files are extremely crucial. The way that they work, anytime a transaction actually changes states from one state to another, it gets logged. The log file in a database is logging every single transaction state from one move to the next. So I'm going to contain the ID of the transaction, what state it's in, and then any data modifications that were made, any writes. I don't really care about the reads because that doesn't change my data in any meaningful way. I care about the writes. So what pieces of data have I manipulated as part of this transaction? That's all included as part of my log. This log file then becomes an extremely useful component. If I ever need to roll back a transaction, what am I going to do? I'm going to look up the transaction ID in the log, view all of the changes that it's made so that I know how to go back and undo them, right? It can also be used for recovery purposes. Let's say I have a power outage or I have some kind of a failure. If I have this log file, I can retrace my steps and redo the transactions that took place since the last time I did a backup. So I can recover some of my data by using this log file. It's an extremely, extremely important part of the transaction management process. All right. This is an important slide. So, transactions are often defined as having what's called ACID properties. And you can see ACID is an acronym. Stands for the four properties that you see up here on this slide. I've already talked about some of these. Some of these we haven't touched on yet. Actually, the first one we have talked about, atomicity. What is that referring to? Yeah. Yeah. The transaction is treated as a whole unit, right? I can't subdivide it into smaller pieces. That's what we mean by atomicity. It's an atomic unit. Okay? Consistency preservation. This is a tricky one. We haven't talked a whole lot about this yet. But what consistency preservation it really is referring to means that when I start a transaction, or before I start a transaction, my database is in what we would call a consistent state. The data all makes sense, right? There's no conflicts, there's no misleading information in my database. After I run a transaction, it should be in a consistent state as well. In between that time, it might be inconsistent because as the transaction is running, right, if it's only partially complete, my database may temporarily be in an inconsistent state where the data does not necessarily make sense. It doesn't match. It's not consistent across tables or even within the same table, right? But after that transaction has ended, I should be back in a consistent state. Does that make sense? All right. Isolation. It's a pretty easy term to define, as it relates to English, but in terms of transactions, what that means is that every transaction is operating as if it's the only transaction in the world, right? We know that's not true. We know that there are lots of users executing transactions on my database at the same time, but those transactions have no idea about the other transactions that are executing. As far as the transaction is concerned, it can only see what's going on inside of its little bubble. It has no idea about what's going on in the outside world. That's actually true for your users as well, right? As for the people using your database, if they run a transaction, They expect that transaction to run exactly the same, whether it's the only transaction that's running on your database or whether there are 100 other transactions running on the database. They don't care, right? That's what we mean by isolation. And last but not least is durability. What durability means is that once a transaction has finished, it's been completed, it's been committed, that we really mean it, right? We really mean that it's been committed. That data is going to stick around. It's very, very difficult to undo a commit. In other words, once a transaction has committed, it says that it's done what you told it to do. You can't undo that commit. And the way that we enforce this is by using what? Something we already talked about. Rhymes with bog. The log files. The log files. We make a record of every transaction in the log. That provides durability to our transactions, right? If anything ever happens, I can go back to the logs and see exactly what every transaction on the system did, and I can recreate that if necessary. So I'm never going to lose a transaction. I'm never going to lose that piece of information once it's been executed. Are there any questions about this? Yes?
Can you roll back?
Can you roll back to delete? Sure.
So
Yes.
Where would you store this?
Where would you store the delete information? You would store it in the log. The log actually contains a list of every piece of data that has been modified and how. Which sounds like a lot of information, right? And it is. Log files get to be huge on databases. And so that's something that's, it's a little bit of a tangent, but one that's worth talking about, right? If I have a database that's got lots of users who are making changes to the database, my log files are just going to explode, right? And the answer is yes, that is true. That is correct. But we have other ways of controlling that situation. Specifically, I'm periodically going to take backups of my database. And once I take a backup of my database, once I am confident that I have a backup, I can toss the log file. It's no longer necessary anymore and start a new one, right, for everything that has happened since the last backup that I took. So if you're taking regular backups like you should be, your log files are only going to be growing for, however often it is in between backups, which might be daily or should hopefully be at least weekly at a bare minimum. So even though they do grow fast, we're going to empty them out every time we make a backup. Great question. Any other questions? Any other questions? So really, if I want to know the current state of my database, right, or if I needed to recreate the current state of my database, I have to find the last backup and the most recent log file. I need both of those things if I want to truly back up my database. All right. So everything that we've talked about so far leads us to this. This is what we're going to spend the rest of the time talking about, and this is actually going to be something that you're going to need to get familiar with for the next homework assignment. We understand transactions, or I've at least introduced the concept of transactions to you, and now we have to figure out how to manage them. If I'm a database, if I'm writing a database, and I'm expecting these transactions to come in, I now have to decide, all right, how do I schedule these things? How do I run these transactions in such a way that it's going to avoid the kinds of issues that we talked about as much as possible? That it's going to keep my database consistent. So the process of taking transactions and deciding what order to execute those operations is called a schedule. It's called a schedule. We want to utilize interleaving if we can. I don't just want to execute the entire transaction one after the other after the other. Why not? Yeah. It's a performance consideration, right? It's a performance consideration. If I submit a transaction and there's 100 other transactions ahead of me in the queue, right? I'm going to have to wait a really long time for those transactions to filter out, potentially. If I do interleaving, it's going to give me more flexibility in terms of how fast I can get those transactions finished up. It might be such that one table is consumed, right? It's too busy. It can't actually handle any more operations. If I'm allowed to interleave other transactions in, I can do stuff in other parts of the database and wait for that table to get freed up again before I do any more work on it. So interleaving is very important from a performance perspective. We want to utilize interleaving of transactions. I want to take the operations and mix them together. But I need to be careful about it. I can't just do it arbitrarily. I need to do it in a way that makes sense, that's going to avoid the kinds of problems that we talked about. We also have to maintain the order. If I'm given a transaction that executes statement A and then statement B, I can't flip the two, right? The programmer submitted them to me in that order for a reason, and I can't just assume that the order is not necessary. So I have to maintain the order. So here's an example of a notation that we might use to write some schedules. We've actually already seen these schedules in graphical form a few slides back when we talked about these kinds of problems. The lost update schedule, right? So how do we interpret this? So SA, that means schedule A, consists of R1X. So that means transaction number 1 is reading item X, right? Transaction number 2 is reading item X, right? Transaction number 1 is writing item X. So that's what we expect to see in a transaction if I'm going to write it out. It almost looks like a formula, right? It's not, but it kind of looks that way. Make sense? So I'm interested in how do I create these things in such a way that I avoid actually the lost update or that I avoid the temporary update. How do I create these schedules to avoid these kinds of issues? So what are we really avoiding? We are avoiding conflicts. A conflict is defined as operations from two different transactions that access the same item, and one of those operations is a write. One of those operations is a write operation. So we really have two types of conflicts that we're interested in. One transaction is reading an item that another transaction is writing to, or I have two transactions that are both trying to modify the same item. And I think you can reason about it, think through it, right, and see that, okay, yeah, I can see how both of those situations could potentially cause problems. Cause exactly the problems that I introduced at the beginning of class today, the lost update problem, things like that. So when I'm creating a schedule, I have to be aware of these conflicts. Now I want to make it very clear, right? I cannot avoid these conflicts. These conflicts are going to be unavoidable. They're going to exist in just about every schedule that I create, right? But I'm just going to be aware of them, and I'm going to try to do something. I'm going to try to manage them in a particular way. So let's take a look actually real quick. Whoops, that's way too far zoomed in, sorry. Let's take a look real quick at some example schedules. So I'm looking at schedule A right here. You can see that it does all of transaction 1 followed by all of transaction 2. This is what's called a serial schedule. It's a serial schedule because there's no interleaving happening, right? There's no interleaving. I run all of one transaction, then I run all of another transaction. And I think that most people would agree, and I hope that you would as well, that if I run transactions like this, I should get a reasonable outcome. If I take every transaction and I run it as an entire unit before running another transaction, I should get reasonable outcomes. I should not run into any problems with this, right? And so I could do it the other way. I could run all of transaction 2 and then all of transaction 1. That's another example of a serial schedule. And again, if I do things in this way, I should get reasonable outcomes. But that's not the kind of schedule we want to create. We want to take performance into account. We want to run our schedules in an efficient way. So I don't want to make serial schedules. I want to make non-serial schedules. I want to make schedules that look like this. These two down at the bottom, where I take the operations and I mix them together. The question that I have, though, is, all right, how can I do this in such a way that I know that the outcome is going to be okay and I'm not going to run into a loss update problem or a temporary update problem or something like that? How can I do that? And so we have a technique. We have a technique. We are going to try and create non-serial schedules that produce the same conflicts that exist in a serial schedule. Think about that for a second. These are serial schedules, one transaction after the other. Conflicts still actually exist, and you can justify that, right? This transaction is reading to the same data item that another transaction is writing to. That is a read-write conflict that exists. So there are conflicts that exist in these serial schedules. If I can create a non-serial schedule that has the same conflicts in it, the same kinds of conflicts in it, then I'm going to say that that's good, that that's a good schedule. I would call that a conflict equivalent schedule, right? It's a non-serial schedule that is conflict equivalent to a serial schedule. Or another term that we would use to describe it is, we would call that schedule a serializable schedule. It's going to produce an equivalent outcome to a serial schedule, even though it is not a serial schedule. Does that make sense to everybody? Right? So how do we do this? We've already talked about why serial schedules are considered unacceptable. It's performance. We're trying to get best performance out of it. So we want to use these non-serial schedules but guarantee the same outcome. We're going to make serializable schedules that are conflict equivalent to a serial schedule. But how do we define this? How do we actually figure this out? That's the question. Well, we have an algorithm. We have a test. And here it is. For each transaction that's part of the schedule, I'm going to create a node. We're going to create a graph. So the nodes in my graph, I'm going to have one node per transaction that's part of my schedule. The edges are going to represent conflicts. The edges are going to represent conflicts between transactions. So you can see that items 2, 3, and 4 are really just defining conflicts. 2 and 3 are defining read-write conflicts, and 4 is defining a write-write conflict. So they're very similar rules. So if we look at rule number 2, it says, for every case where a transaction executes a read item after a different transaction executes a write item, I'm going to make an edge between those two nodes in the tree, or in the graph, sorry. Rule 3 is the same thing, but in reverse. I do a write first and then a read. And then rule number 4 is if I have 2 writes. I'm going to go through an example here in just a moment. So once I've gone through this process, step 5 then says, all right, look at your graph. If there are no cycles, then it's a serializable schedule. If there is a cycle, then it's not serializable. It's a bad schedule. It is not conflict equivalent to a serial schedule. Think about the implications of this, right? If I run this algorithm on a serial schedule, I should never get a cycle, ever. This algorithm is telling us that serial schedules will never have a cycle in the graph. Yes?
Well, what's a cycle?
A cycle means I can take a loop from one node back to itself. by following the edges in the graph. So there's a circle. The graph connects back to itself. I'll draw some examples up here on the board, actually. In fact, why don't we go ahead and do that now? Let me just double check here real quick. For each case, so we're drawing the edges from the earlier item to the later item. The edges are directed. That's important. The edges have direction. So we're always drawing the edge from the earlier item to the later item. All right, let's do an example. I'm going to do an example we'll do an example on a serial schedule for starters. So here's our serial schedule. The first thing that the algorithm tells us to do is to make a node for each transaction. All right, I've got two transactions, T1 and T2. So let's make two nodes. And now I need to start looking for conflicts. So what conflicts do you see in this schedule? Somebody point one out? I actually pointed one out a little bit earlier when I was looking at this schedule. What conflicts exist? Yeah.
T2 does a read item after T1 does the write item to X.
T2 does a read item after T1 does a write item to X. So that's a write-read conflict or a read-write conflict, however you want to say it. And so the algorithm says, all right, the write item, so you're pointing out this write item here and this read item here as a conflict, which they are. So the algorithm says this happens first, so I'm going to draw an edge from T1 to T2. From the earlier item that takes place to the later one. What other conflicts exist? There are more. Yes?
Is the read write also?
The read write. So T1 reads this item X, and then T2 writes it. It's another read-write conflict, but you know, the operations have been reversed, but it's still a conflict. Yes.
Does this mean that every time you have like a write-write conflict, you have to have two read-write conflicts as well? They have to read them.
Every time you have a write-write conflict, you have to have two read-write conflicts. That is an interesting question. I haven't thought about that. I mean, I am kind of leaning towards yes, but I also, that's more of a gut answer. I don't have a definitive proof one way or the other. It would be an interesting little proof to try and sketch up, though. Yeah, I don't have a definitive answer on that. That's a great question. If we go back to this conflict, so I have a read item from T1 conflicting with the write item in T2, and so the algorithm says, all right, whichever operation happens earlier, which is this one, I'm going to draw an arrow from this transaction to this transaction. Well, I already have it from the other conflict that we just did, so I don't need to add another one. It's already there. And that's going to happen a lot. I'm actually going to see multiple conflicts happening between the same transactions. That's not unusual. Any other conflicts? The answer is yes. There is one more conflict. Yeah. Right. So I see both of them writing to the same item. Same story. I look, this is the one that happens first, so I'm going to draw an edge from T1 to T2. Well, okay, we already have it, right? It's already there. And I'm done. That's it. Those are the only conflicts that I have, right? So now I look at my graph, and is there a cycle? If I start at T1, can I make it back to T1? No, I can't. I would need another edge going back the other way, right? With two transactions, your graphs are very simple. Very, very simple. I'm either going to have an arrow pointing this way, an arrow pointing this way, or both. Those are my options, right? If I ever have both, that's a bad schedule. If I just have one or the other, that's okay. This is an okay schedule. And guess what? It's a serial schedule. Of course it's serializable. If we had gotten a cycle here, we would have had big problems. Had very big problems. This is a serial schedule. This is what I expected to happen. Are there any questions about this process? So things get more interesting when you look at non-serial schedules. So if I go back to my slides here. So these schedules down at the bottom, schedules C and D, are the ones that are probably a little bit more interesting, but I'm going to let you guys do that. So I want you to take a few minutes and look at, well, this slide doesn't help you at all. I'm going to put this other one back up with the schedules on it. I can zoom in on them. Look at schedules C and D and go through the conflicts graph for each of these schedules. And then once you're done, be able to tell me, are they serializable or not? I'll give you a few minutes. I'll be around if you have any questions. Let me know. Yes, because well, actually, T2, so in both of these particular situations, T2 gets bid earlier as soon as it's done, as soon as it executes its last operation. Doesn't matter. So really, though, the way you draw it, if you draw it like five-sided instead of writing it
That makes sense.
my argument yeah, I know the algorithm. Yeah, so that's think about what that really means. That means that even if I the transaction in a serial way, still have. How do you grade it?
Yes. We're not saying that we are going to create a schedule just now. We're saying we're going to create a schedule that has the same kinds of problems that we have. Is there an advantage in having a serializable leaving that situation over having every yeah, it's all about performance, right? You're probably that allows me to do, potentially more operational stuff. They can more essentially process on Thursday. But other comments I would into is I have a lot of operations in the same team. I won't be able to do any more operations. But I have other operations. I can do those within the time. Put more of those. Instead of just sitting there waiting.
All right. Let's make a couple graphs. These aren't too terribly tricky, but it's a good practice. So let's do one for C. Oh, wait, what are you? All right. Here's schedule C. I want to make a graph. So I'm going to start with my nodes. That's the easy part. One node for each transaction. So here's T1, here's T2. All right, what conflicts do I have? Kind of the same ones, right? It's the same two transactions. I have the same conflicts. We just need to pay attention to how they get added to, or do I? I don't know. We need to see. So conflict, yeah. Okay. Right. So the read item here in T2 and the write item in T1. And so the algorithm says we always want to draw the arrow from the earlier operation to the later one. So that's saying from T2 to T1. Right? All right, what else we got? Yeah.
The very first read item T1 to the write item T2.
Yep. So there's this conflict here from read item to write item. And so again, the algorithm says, all right, from the earlier one to the later one. And so that's saying to draw an arrow like this. And actually, at this point, we're done. We could look at the other conflict, which is a write-write conflict from here to here, right? It would have us draw the exact same arrow that we just drew. So this is our final graph, and this is a problem. We have a cycle. We have a cycle. This is not a conflict serializable schedule. It's no good. It's a bad schedule. All right, well, let's try the last one, D. All right. Again, what are you? Here's schedule D. I'll draw my nodes. And we're going to see the same kinds of conflicts show up, right? I see the conflict from read item X to write item X. So that tells me to draw an edge from where to where? T1 to T2, right? And then I see another read item here, right? To a write item here. Nope, sorry, wrong. That's a Y. I can't read. My apologies. Actually, I see a write item here to a read item. That's the one I was looking for, right? That's the same one, though, T1 to T2, correct? And then I have this write-write conflict, which again is T1 to T2. This schedule's good. This schedule's good. This is a serializable schedule. But we can actually go deeper than that. We can talk about this in a little bit more detail. I know that it is equivalent, conflict equivalent to a serial schedule. But I can actually prove it, right? How do I know that it's conflict equivalent to a serial schedule? I can make this graph for the serial schedule, and if I get the same graph out, right, of a serial schedule that I get out for this one, that's the proof right there. They are conflict equivalent. They produce the exact same conflict graph. In fact, this is the exact same conflict graph that we created for Schedule A. Right? I'm pretty sure I still have it up. Maybe. I don't know how to use this program. There it is. Schedule A. It's the same graph. It's the same graph. So I can go farther. I can say not only is this conflict serializable, it is conflict equivalent to this serial schedule in particular. Generates the exact same graph. Does that make sense? So one other thing to point out, if I go back to this Schedule D real quick, we've actually seen this schedule before. What schedule is this? Somebody pointed it out to me during break, or while you were working. We've seen this before today, in a previous slide. Anybody remember? Maybe it wasn't exactly the same. It was certainly very close. Let's go back and review. Not incorrect summary. This. Temporary update. Schedule D is basically this. It's this, right? So think about that for a second. Think about what we're doing and think about what that means, right? At no point today have I made a claim that we are going to avoid these problems altogether. And if I did, that was a very dumb thing for me to say, so ignore it because it's not true. You know, we're going to run into these problems. It's going to happen, right? What we're doing with the serializable checks by making the graph and everything, we're not saying that we're going to avoid all these problems. We're not saying that temporary update problem is never going to happen. What we're saying is that we'll run into the same kinds of problems that we would have run into if we'd executed these transactions serially, one after the other. That's what we're saying, right? Does that make sense? Are there any questions about that? Yeah.
So this is serializable. What even is problematic about this?
What even is problematic about this? I mean, the problematic thing about this is, oh, my pen's not working, is the fact that this update here almost looks like it never happened. It's a temporary update. As far as we're concerned, it never happened. But think about that. I mean, that happens all the time. You make an update to a value, I come by 2 minutes later, I change the same value. It happens all the time. Happens all the time. What's confusing about it is when you, who made the original update, come back after I made my changes, and you look at the value, you're like, I just changed this a second ago, and now it's different. That's where the problem comes in, right? But it's unavoidable. Sometimes it's unavoidable. So I'm not making the claim that these problems will never happen. But we do want to avoid them as much as possible. And we do want to create schedules that will sync up with serial schedules. Any other questions? How are we doing on time? Oh, we're doing great. Any other questions? Yeah.
On that last one, there was no read of why beforehand, like that temporary update problem.
There was no read of why.
So like that was
it'd still be the same problem. Yeah, it'd still be the same problem. Fairly certain. It becomes a worse problem if transaction 1 reads the same value in the same transaction. It becomes worse, but we actually have a different name for that. That's called the unrepeatable read problem. When I read a value and it gets modified, and then I read it again, and I see it's different. Is there another question over here? You good? Or question?
Yeah. When you were making the precedence graphs, it seemed like in your examples there were 3 instances going from T1 to T2, but you only need to draw 1 arrow for that.
Yeah, I mean, as far as a graph is concerned, if 2 nodes are connected, they're connected. They can't be like triple connected, you know, not in the same direction anyway, right? Any other questions? So we've got this test. We can check to see if, we can check to see if a schedule is conflict serializable or not. But let me give you a little bit of a sneak preview of what we're going to be talking about on Thursday. In practice, right, on an actual database, that conflict serializable test is not really used. Why not? Why wouldn't we use that test? What's the problem? Yeah.
You can't predict what other transactions people are going to make, only your own.
Well, the database knows what transactions exist, though, right? So the database has a pool of transactions that it wants to execute. Theoretically, we could do this. It's not impossible. We could do it, but we don't. Why? Yeah. Time. I mean, that's almost always going to be a good answer to a question like that, right? We made a graph with 2 transactions. It's a very simple graph. That's not a very practical example, though, because in the real world, I'm going to have hundreds, thousands of transactions and more coming in all the time. So to create a graph like that and maintain a graph like that, to perform the analysis like that, is very time-consuming. And then think about what happens if you do complete the graph and you detect a cycle. Guess what? Now you have to throw the whole thing out and start over again with a different schedule and check it. And then repeat that process over and over and over again until you find a schedule that doesn't produce a cycle, right? Could we do it? Yes, absolutely. Would it work? Yes, it would work. It would be very slow. It would be very time-consuming and resource-intensive to create those graphs. So we don't. And without giving too much away, we're going to talk about a technique on Thursday that says, all right, we understand that we want serializable schedules, but I don't want to just use this guess and check brute force method. Maybe there's a way that I can actually generate schedules that I know are serializable. I don't have to check whether they are or not, because if I create them in this particular way, I know for a fact that they are serializable schedules. There is a way to do that. That's the topic for Thursday's class. But to wrap things up for today, we can talk about how to do this stuff in SQL in practice. So what does this look like in code? Transactions are a very practical thing that you can use and should use in your code. The way the implementation works varies depending on what database you're using. This is MySQL, since that's the database that we've been leaning on the most in this particular class. And it's pretty straightforward. You say start transaction, and then once you've reached the end of then you start listing out the statements that you want to execute. And once you've hit the end, you say commit. That's it. If at any point you want to manually call a rollback, you can actually use the word rollback in your transaction. It will cancel the transaction out. A lot of times, though, it's not necessary. A lot of times, if an error occurs, the transaction will just perform a rollback on its own. You don't have to actually explicitly tell it to do that. But the option is there. You can do that if you want to. Now, the other interesting thing to keep in mind, right? If you've been doing the studios and stuff like that, we have not been using transactions. I would not have expected you to use transactions to complete those studios. But guess what? You actually have been. If I execute a statement on a database, it gets wrapped in a transaction, whether I say I want it to be inside of one or not. So even if I just execute a single statement, it's going to wrap that single statement inside of a transaction and execute it every time. So when do I really need to specify this out? I really only need to explicitly use transactions on my database when I have a lot of statements that I want to be grouped together in a single transaction. That's when it becomes necessary for me as a programmer, as a database user, to explicitly use transactions. Any questions? And so then last, but certainly not least, we've got this concept of an isolation level. So what an isolation level does is it allows you to bend the rules a little bit. So I introduced the problems that you might run into with transactions, like you can see non-repeatable read is on this list, right? Or a phantom read is on this list, right? And so we can tell the database that we care about those things and we want to avoid those situations. And the database will use that when it creates schedules to try and avoid these situations as much as possible. That's going to lead to schedules that are not as efficient as they could be. Think about that for a second. If I relax the kinds of violations that I care about, the scheduler then, when generating schedules, might be able to find schedules that can run faster because they're not as concerned about breaking these rules, right? They're not as concerned about these kinds of problems that might pop up. And so we actually have a way of interacting with the database and telling it how much we really care about these kinds of problems. If I'm worried about data consistency, that is my primary goal, then I want to keep the isolation level at its maximum limit, serializable, right? That's the maximum limit that's going to prevent the most problems from occurring. If I care about performance and I'm just trying to get data moving as fast as possible, and I'm willing to sacrifice even the consistency of my data to make that happen, then I can turn the isolation level down. You can see the different levels here, right? We've got actually, so the violations, a dirty read is reading data that has not actually been committed yet. So think about what that means. I read a value and I'm taking a big risk because if the transaction that modified that value fails, then that value that I just read is going to disappear, right? So that's a big risk. That's called a dirty read, reading a value that's not been committed. Non-repeatable read we talked about. Non-repeatable read is when I read the same value twice and I get a different value back each time. So it's not repeatable. And then a phantom read is when, oh shoot. You know what? I'm blanking on this one. I'm just going to have to Google it. Computer? No? Doesn't like keyboard. It's in tablet mode right now, sorry. Got to use the touch screen.
It says a phantom read occurs when in the course of a transaction, new rows are added or removed by another transaction to the records being read. This occurs when brain function not a part of. Yeah.
The first sentence was good. Thanks. Appreciate it. Yeah. So it occurs when new stuff's getting added in as I'm reading through a table, right? That was the main gist of it. Yeah, that makes sense. So it's like they appeared out of thin air, right? I go to read a table, I'm expecting a certain number of rows out, and then all of a sudden I get these phantom rows that appear out of nowhere, right? Because the transaction's making those modifications. So in the most strict sense, I wouldn't count those rows until after the transaction is fully committed. But what the isolation level allows us to do is say, well, actually, if you want to read those before they've been fully committed, you can, right? You just have to tell the database that that's what you want to do. And so these isolation levels go from, the most strict down at the bottom, a serializable isolation level is as strict as it gets, to the least strict, which is read uncommitted, which is like the Wild West out there. Do whatever you want. I don't care. Just get the job done, and we'll figure out the rest when we have to. So it's a trade-off. And then we've got things in between, right? Where, okay, maybe I want to get some extra performance, but I don't want to get too crazy with the data inconsistencies, right? I can pick an in-between level of isolation. It's called isolation level for a reason, right? Think back. Where else do we see isolation today?
Acid.
The acid properties. It was one of the acid properties. That's what the I in acid stands for. Isolation meaning that each transaction thinks that it's the only transaction, right? It doesn't know about the other ones. Well, if I manipulate the isolation level, I'm affecting that. I'm saying, well, okay, now I'm actually reading stuff that other transactions have not committed yet. That's not isolated anymore, right? I am now somewhat aware that there are other transactions modifying that data, and I'm reading that modified data as those transactions are executing. That's what it means to modify the isolation level. I'm tweaking that property of my transactions. Any questions? Any questions? All right, that's all I had for today. We'll pick it up on Thursday with concurrency issues, so I'll see you then.